Hello and welcome to Coast and Country, powered by the science of the Connecticut Agricultural Experiment Station. Coming up in this special edition all about PFAS, the forever chemicals. Dr. Sarah Nason talks about her work and findings around biosolids and fertilizers. Shelley Stanley of Upland Grassroots explains how the Micmac tribe in Maine are using hemp to clean up their contaminated land. And Dr. Nubia Zuvezamena and Dr. Sarah Thomas explain their work around phytoremediation and nanomaterials. But first, what exactly are PFAS? We keep hearing about them in the news and millions of dollars are being pledged to research them more and how to clean them up. Dr. Sarah Nason of the Connecticut Agricultural Experiment Station breaks down what PFAS are and where they come from.
PFAS is an acronym. It's short for per- and polyfluoroalkyl substances, and it's a group of molecules that are used in a lot of different products. So they've been in use for a long time, since about the 1940s, and they're really especially useful to make coatings on things. So they can be waterproof, they can be greaseproof, so they end up on things like carpets and food packaging and raincoats and boots and anything else you can imagine that you would want to be waterproof or greaseproof. They're used as a surfactant in firefighting foams, and that's been a really useful life-saving technology. So they have a lot of useful properties and they're very durable molecules, and that makes them useful and that's great, but unfortunately that means that when these products meet the end of their lifetime, or that when the firefighting foam gets sprayed all over the environment, the PFAS molecules stick around. They stick to soil, they leach into water, and they don't degrade over time. So since they've been in use for a long time, they're accumulating in the environment. And recently there's been more publicity about the very bad health effects that PFAS have. They can cause a whole variety of different health problems when people are exposed to them. They come from industry products mostly, and where we see them a lot now, we see them in wastewater, we see them leaching out of landfills, but in order to get there, they come from the products first. We also see them at sites where there have been fires or where firefighters have been training. So that's at a lot of places like airports and military bases are common pollution sites. And places where PFAS have been manufactured are some of the biggest ones. But because they've been used in so many products, they're pretty ubiquitous in the environment these days. You can find them almost anywhere you look. Most chemicals that get released into the environment, they'll degrade over time. Like if you leave them for long enough, the molecule will break down and eventually become harmless. PFAS were designed to be ultra durable, and at the core of their molecular structure is carbon-fluorine bond, and that's the strongest bond in organic chemistry. So that means these molecules do not degrade over time. They stick around, theoretically, possibly forever. So biosolids are a major concern for the state. They're really a concern all over the country. Biosolids are land applied. They're made out of sludge that comes out of sewage treatment plants. So they have all sorts of different chemicals in them, and PFAS are just one of them. But they're of concern because there have been some farms, particularly in Maine, where they've done a lot of land application of biosolids and then found very high levels of PFAS in the product produced by the farm. In Connecticut, we want to make sure that's not happening here. So we're starting at CAES by analyzing the biosolids and biosolids-based fertilizers that are sold within the state to see how much PFAS is in there. So if the PFAS are in the biosolids and the biosolids get spread out over the land, they typically don't just stay there. Once there's, rainwater flowing through the biosolids and through the soil, some of the PFAS can dissolve and then they can move where the water moves, and that can be either into the groundwater or up into plants. And then if cows eat those plants, or if cows, have incidental dirt eating, they can also get PFAS inside of them, and then it can get into the milk. So once the PFAS are on the farm, they really can move quite a bit. PFAS is an enormous class of chemicals. Over 10,000 of them exist. And typically we don't look for that many because it's a real challenge to look for that many. The EPA methods that look for PFAS have a maximum of about 35 on their list, and so we usually focus on those. And Connecticut has focused on 5 PFAS in particular in their recommendations about drinking water. So those are the ones we've been analyzing most closely in biosolids. We have an instrument, it's called liquid chromatography coupled with tandem mass spectrometry. And we have a very special one of these instruments. It's a high resolution mass spectrometer. So that allows us to look for a really wide range of contaminants at once. Like I said, the typical methods look at, maybe 35 contaminants, but we can potentially look at a lot more with this instrument. It's expensive and it takes a lot of training to use, and that's one of the things that's challenging about PFAS analysis in general, is not a lot of labs have this capability. So we're lucky here that we have the technology that lets us do that. And PFAS are everywhere. They're in a lot of products still in use. So we also have to be very careful about what's in our lab to make sure that our lab isn't contaminating samples that come in. We have separate supplies and we make sure we look at what everything is made out of before we do PFAS analysis. It's an extra challenging thing to look at in the lab. There's definitely evidence pointing in the direction that many PFAS are dangerous, but they come in a lot of different forms. Some of them are small molecules that get used in coatings, but increasingly we're also seeing things like fluoropolymers, like plastics that have a lot of fluorine as part of their molecular structure. And there's not a lot of toxicology studies on that yet. There's other technologies that are coming out for PFAS, things like sorbents you add to soil that will bind the PFAS and keep them in place and keep them from getting into the water taken up by plants. But that also doesn't fully solve the problem of the contaminants being there. One thing that we've been looking into in our research here is phytoremediation, which is where you use plants to clean the soil. So you use plants in particular that will take up a lot of contaminants. And then this is a phytoextraction method. If the plants take up the contaminants, and you can take away the plants and you've removed your contaminant from the site. So we're looking into the possibility of using that method to clean up PFAS because it's fairly approachable, it can be inexpensive, and you could do a very large volume of soil that way.
In early 2019, a community group in the state of Maine reached out to the Agricultural Experiment Station to talk about phytoremediation at a former Air Force base in the northern part of the state, using hemp to clean up PFAS contamination at the site. The project is ongoing, and I caught up with Shelley Stanley of Upland Grassroots, who started the project on behalf of the Micmac tribe, who are the owners of the land, which was handed back to them by the federal government.
So we're basically, testing fiber hemp's ability to clean contaminants from the soil. And we started working with the Connecticut Agriculture Experiment Station in the beginning of this project and started working on PFAS, which was sort of a coincidence. Like that wasn't what we, intended to do, but it was what the scientists in Connecticut were most interested in. And I think it was a great decision to work on PFAS, because of the emerging crisis. So we've been growing hemp there since 2019 on a site that used to be a firefighting site for the Air Force base. So they would basically put huge things on fire in the middle of this parking lot and then, use AFF foam to put it out. And it all drained into this one area of the parking lot that drains into a stream. So there's a lot of PFAS in that specific area, and that's where we're growing the hemp now. It is going really well. I mean, we've gotten a lot of data over the last couple of years with, Connecticut Agriculture Experiment Station and also some other institutions that we've started working with. So we found that, the PFAS in the soil is decreasing. The hemp is taking up PFAS, and quite a lot of PFAS we're finding recently. And it's also distributing it throughout itself. So it goes into every part of the plant, including the pollen. So, we now harvest before the plant goes to flower. And yeah, there's definitely a lot of challenges, I would say, but some sites won't have quite as many challenges as we do. Watering is a huge challenge there because we can't use the groundwater or surface water. It's also very contaminated with many different things. So we have to bring in water every time that we're watering the plants, which has made it difficult to scale up there. We also haven't scaled up that much because we don't want to dispose of the plants like in a landfill or something, where we're just moving the problem from place to place. So we've only been growing enough to give to the scientific institutions that we're working with so that we don't have to, dispose of it. But once we have a way to break down the PFAS in the plant, then, of course, we can all scale up like on a large level and grow a lot of hemp, and then it would get rid of the PFAS at the end if we find a process that can do that. They were initially told that, it had been cleaned. So their understanding was that, it had been cleaned to a safe level that they could use it without fearing for, getting contaminated themselves. But then they found that actually that wasn't really the case. There's a lot of problems at the site with many different chemicals, petrochemicals, PCBs. PFAS just emerged out of nowhere in the last couple of years as being, a huge problem at that site and on their land specifically. So, they have been very interested in cleaning it up. And, the unfortunately, we make a lot of chemicals that nobody knows how to break down, very well, like DDT or things like this, so there's this problem, especially at that base where so many chemicals were used that they don't really know what to do with. So for the Air Force and the EPA, it is kind of like they don't have the technology to clean it. And they've said many times, the Air Force has said, if they have something that can clean PFAS, then they would use it. So they've said that they were interested in hemp and, that if it works, they would like to, potentially use it on that site and other sites. So yeah, the Mi'kmaq Nation, that's their ancestral land. And they're going to be there, their headquarters for their tribal government offices is in Presque Isle, which is, maybe 20 to 30 miles away. So they're going to be there forever, so for them, it is very much in their interest to clean it, even if it takes a long time and is a slow process. Whereas, I think people that are not necessarily from that land or they're going to stay there, we tend to think of things in a more short-term way, like, oh, if we can't clean it in 5 years and cheaply, it's not worth it. Whereas for them, like, of course, it would be worth it to put in the time. Even if it takes several generations, like then they know it's clean enough, for them to use safely.
This project emerged from a previous pilot project that we had with the community up in Maine, and it was a phytoremediation project. We saw that plants were taking up some of the PFAS and that the soil was diminishing, well, the amount of PFAS in the soil was diminishing. But we saw some of the limitations of that we needed to improve the efficiency of the phytoremediation so that some of the PFAS that are more abundant the plants could uptake those materials. So for that's when this project emerged. We formed a team with Yale and the University of Minnesota, and we put together a project that got funded from NIEHS, the National Institute of Environmental Health Sciences. And this is to use nanotechnology. In this case, we're using nanomaterials because nanomaterials are very tiny materials that can go more easily into the plant. And also we can change the surface of these materials so that they have an affinity to go easily into the plant. So to answer your question, we're developing materials that have an affinity both for PFAS and both for the plant. So these nanomaterials, the intention is that they can have an affinity for both and to enhance the phytoremediation project so that the materials can bind to those PFAS that have less affinity for the plant, but they go into the material and then make it easier for the plant to remove them from the soil.
I use the nanomaterials developed from the Christie Hicks groups, like carbon dots. We work on carbon dots and ultra mesoporous nano silica materials, which is actually used in the phytoremediation. So what happens here is that we use hemp plants here for the phytoremediation. Why we use hemp plants is that the hemp plants having a lot of biomass, and we actually grow them in hydroponic methods, and we add the nanoparticles to our hydroponic solution, which actually give the nutrients to the hemp plants. And then we want to know what happens when the nanomaterial is, as the hemp plant is growing, how it helps the nanomaterial, how it helps the PFAS to uptake. So that's what we're working on in the project now.
This variety uses a lot of water, so it's easier for the movement of water is what brings things into the plant. And another thing is that this is a continuation, or is a project that emerged from our pilot project with the Mi'kmaq Nation, and they were using hemp, and we already have some basic knowledge on that, and we were building upon that.
With hemp, we are excited because we don't know what is the mechanism happening, how the plants are intaking the PFAS, and so we would like to understand what is the mechanism happening when we introduce nanoparticles to it. How does the PFAS uptake on different chains, like Nubia mentioned, there are small chains, long chain of PFAS. So it's very interesting. We are excited to see the results, especially the mechanism happening with the plants and in the hydroponic setup.
There's another strategy that we're looking into that is the complete opposite, is locking the PFAS in the soil so that they are not coming into the food chain. They are just to contain them and keep them in the soil. So for that, we're developing other materials that it's based on biochar, to have a material that will sorb PFAS and will have an affinity for these compounds, to lock them in the soil. So biochar is a material that is made out of, when you burn, in this case we're burning biomass, we're burning material from plants, and it's based on carbon, and it can work for sorbing purposes. And in this case we're mixing it with other materials. We're making biochar composites that have an affinity for PFAS, so that they can lock them in the soil. When you mix them with the soil, the idea is to keep PFAS in the soil.
So the big thing we've been doing at the station, in addition to the phytoremediation work, is working on methods for measuring PFAS in various things. So that's taken a few different forms. We've helped out with developing and testing a software called FluoroMatch that's an attempt to be able to measure more of the PFAS, attempt to look at, the whole 10,000 molecule category rather than just the list of 35 that's in the EPA methods. And then we've been working on methods for measuring PFAS in different materials. So we've been looking at water, we've been looking at some human blood samples, the biosolids, we have a lot of work on some soils, and we're always continuing to look for new sample types to work on. PFAS are still being released. We're getting, new, slightly different molecules to get around the ones that get regulated. And so there's been some changes in what's getting released, but it's still an ongoing problem. And because the chemicals are so hard to degrade with those carbon-fluorine bonds in the atoms, they're going to stick around for a while. A lot of questions about where are PFAS really necessary to use, because there are applications where they're still necessary. Firefighting foams are life-saving. The fluoropolymers used in some medical devices can't be easily replaced. But there are places where we can use alternatives, things like food packaging. PFAS are sometimes even found in very unnecessary products like ski waxes that could be eliminated. So asking those questions for where are there alternatives, how can we reduce their use and sort of stop the spread of them into the environment, I think those are important questions to be asking right now.
PFAS contamination is not just a problem here in the US, it's a worldwide issue. And as our scientific knowledge about these forever chemicals continues to grow, more money is being pledged to help clean up our environment, and especially the water we drink, to reduce the amount of PFAS we are all consuming on a daily basis to help protect our health. PFAS will be with us for many years to come, and the efforts to remove it will also take just as long. But hopefully, over time, we will better understand this group of chemicals and whether there are safe levels of it or not, so we can all make more informed choices. If you have questions about PFAS exposure or contamination, you can contact the Connecticut Department of Public Health or the Connecticut Department of Energy and Environmental Protection at their websites. Details are on screen now for information and resources that might be available to you. That's all from this edition of Coast and Country. Thank you for watching. We'll see you again soon.